In this video, we'll talk about graphing linear systems of equations with two variables. We're going to determine whether an ordered pair is a solution to start with. So here we have the ordered pair, 5, 2, and we want to know if this ordered pair is a solution to the system. Well, first of all, a system contains two linear equations at the same time. It's possible to have systems that include more than two, but we need to have at least two linear equations. So what we want to know is, does the ordered pair 5, 2 satisfy the first equation and the second equation? So we'll just substitute 5 for x and 2 for y in each of these equations. So we'd have 2 times 5 minus the y value equals 8. 10 minus 2 equals 8. So it looks like 8 equals 8. That's true. That's good. Now we'll substitute 5 and 2 into the second equation. So x is 5 plus 3 times the y value of 2 equals 11. 5 plus 6 equals 11. Here we have 11 equals 11. Since the ordered pair 5, 2 works in both of the linear equations, the answer is yes, 5, 2 is a solution to the system. So in order to be a solution, it must work in both of the equations. In the next example, we're given the ordered pair -2, -7. So x is -2 and y is -7. We'll make our substitutions. 6 times -2 minus the y value, so be careful, it is subtraction of a negative, equals -5. 6 times -2 would be -12, but then this changes to +7 equals -5. So it looks like we have -5 on the left and -5 on the right. So what we know so far is that -2, -7 is a solution for the first equation. Let's try it out in the next one. 4 times x value of -2 minus 2 times y value of -7 equals -2. So here on the left we've got -8, and the product here is +14 equals -2. When I combine -8 with 14, I get 6 equals -2. Well, 6 does not equal -2, so we do not have a solution. -2, -7 is not a solution because it does not satisfy both of the equations in the system. So our answer is no. Now there are three different types of solutions that could occur with a linear system. We could have line 1 and line 2 intersecting at one place or one ordered pair. So you're going to have some kind of an x and y values at that point of intersection. This is called a consistent system or an independent equations because the equations are completely different from each other to form these two lines. With the second example, we have no solution because line 1 and line 2 are parallel, and therefore they are never going to intersect. So this is an inconsistent system. We have no shared solutions. They are independent equations. And the last example is a little harder to tell what's going on here. You can barely see in red there, a little arrow, that's line 1, and the other is line 2. So you can notice line 1 and 2 are the same line. So those are a consistent system and dependent equations. So other characteristics that are important to talk about with these three situations is that back with one solution here, the slopes of line 1 and 2 are different from each other. The slopes for no solution, they would be the same slope, but different y-intercepts. We have different y-intercepts also for the one solution example. The last case here with the same lines, if the lines are the same, then they have the same slope as each other, and they also have the same y-intercept. So let's think about those three different cases, and we're going to take each system given and graph the system to see if we can determine if it has one solution, no solution, or infinitely many solutions. So the way we're going to go about graphing these lines is to put each line into its slope-intercept form. So if I start with 3x plus y equals -1, I want to put this into slope-intercept form. So I'm going to take away 3x from each side of the equation to get y equals -3x minus 1. All right, I'll call this line 1. So I can clearly see that the slope is -3 and the y-intercept is -1. So I'll go ahead and graph that. I'll use the technique for plotting the y-intercept and then using the slope to rise and run. So if the slope is -3, remember that's -3 over 1, so I know to rise, that means I'm actually going down 3 because it's a -3, and a run of +1. I need to start by plotting the y-intercept. So 0, -1 is right here, and I will go down 3 units and over 1, down 3 and over 1. Now remember, that's the same thing as if I had written 3 positive and placed the negative with the 1. So from that y-intercept, I could rise 3 and go to the left 1, and that will help me to draw the line. And now we'll go to line 2. We had -2x plus y equals 4. To isolate y, it looks like we need to add 2x to both sides of the equation to get y equals 2x plus 4. This time my slope is +2, so we'll write that as 2 over 1, so we have a rise and a run. And the y-intercept is 0, 4. So first I plot the y-intercept. From there I rise 2, run 1. Rise 2, run 1. And I can keep doing that. Also, you know how we have been taking subtraction of a negative and changing that to plus? Do you agree that -2 divided by -1 would be an equivalent slope to +2 over +1? So the reason why I would even think about doing that is it helps me to plot some more ordered pairs to the left of that y-intercept. So if I start at 0, 4, I could go down 2 units and left 1 unit. Go down 2 units and left 1 unit. So it just helps to extend the line going in the other direction. So did you notice at this ordered pair it had both a blue dot and a red dot? That must be the point of intersection of these lines. So let's draw the line. There's line 2, and this other line is line 1. So it's clear now to see that they definitely are intersecting lines. There should be one solution, and the ordered pair that both lines share looks like -1, +2. Now if it had been a fraction, it would be almost impossible to guess what the exact answer is, but when you have integer answers, it's easy to tell from the graph. Let's try another example. We have 2 more lines in our system, x minus y equals 5 for line 1, and 2x equals 2y plus 14 for line number 2. So we'll start with line 1, x minus y equals 5. We'll start by subtracting x, -y equals -x plus 5. But this is not quite finished because we have a -1 coefficient. we need positive 1. So to undo multiplication of negative 1, we're going to divide every term by negative 1. Now we have positive y is equal to x minus 5. So this slope, notice there's nothing written in front of x. That means it's positive 1. So the slope is 1. And our y-intercept is 0, negative 5. So we'll plot 0, negative 5. Rise 1, run 1. We'll draw that line, line 1. Now we'll move on to line number 2. This looks different. 2x equals 2y plus 14. Now our goal is to put this into the slope-intercept form because really we want to compare these slopes and y-intercepts with each other. So I think how I'll start is take away 14 from each side. That way I'll get the term with y isolated. So I have 2x minus 14 equals 2y. I'll need to divide every term by 2. So that means x minus 7 equals y. So putting that in order that we're more comfortable with, y is equal to x minus 7. So our slope is 1. Our y-intercept is 0, negative 7. Let's plot that. And our slope is 1. We'll draw the line. Now what do you notice about line 1 and line 2? They are not intersecting anywhere. So let's go back and see if there maybe is a reason why I could make that statement that they're not going to intersect. So it all comes down to comparing our slopes. Notice that the first line has a slope of 1 and our second line has a slope of 1. But the y-intercepts are actually different values. So as long as the slopes are exactly the same, we should end up with parallel lines, and this means that there's no solution to the system because those lines are never going to share a point. All right, in this next example, we have 2x minus 3y equals 6, and y equals 2/3 x minus 2. Now you may notice that this second line already is in the slope-intercept form. So we might as well go ahead and just graph this to start with. Y-intercept is negative 2, and from there we can see that the slope is 2/3. So we're going to rise 2 and run 3. And we'll draw that line. Now with the first line, we'll need to rewrite that. 2x minus 3y equals 6. So I'll subtract 2x from each side to get negative 3y equals negative 2x plus 6. I'll need to divide all terms by negative 3, so I end up with y equals positive 2/3 x minus 2. So this slope is positive 2/3. The y-intercept is 0, negative 2. Well, that's exactly the same as line 2. So the y-intercept is already plotted. If I rise 2, run 3, see how I landed right on the line? If I rise 2 and run 3. So line 1 and line 2 are the same lines. We can see that their y-intercepts, negative 2 and negative 2, are exactly the same, and they each have a slope of 2/3. So when we compare the slopes and y-intercepts of lines within each system, that can give us a clue about what kind of solution we should end up with. So when we have the same slope and the same y-intercept, we have the same line. When we have different slopes and different y-intercepts, we have one point of intersection. And when we have the same slopes and different y-intercepts, we have parallel lines.